Hi, welcome to Algebra 2 Common Core. Today in lesson number 2, we're going to be introduced to a new way of measuring angles, a new unit of measure called a radian. So just as we can measure lengths with different units of measurement, for example, we could measure by centimeters or by feet or by yards, we would of course look at the most appropriate way of measuring. For example, if we have a football field, we don't want to measure it in centimeters. It would be more appropriate to measure it in yards. So for angles, there are also several ways in order to measure the angle. So for us, we know how to measure angles in terms of degrees. Today we're going to be taking a look at measuring our angle in terms of what is called a radian. So let's start with the definition of a radian. You might want to pause the video and write down this definition. A radian is the measure of an angle that, when drawn as a central angle, intercepts an arc whose length is equal to the length of the radius of the circle. So we've got our diagram here, which of course shows part of a circle. It's a sector of a circle. It would be like looking at a piece of pizza or a piece of pie. The angle is right here, touching our vertex A. Now, this angle would have a measure of 1 radian if the radius of the circle that we were using exactly equaled the amount that we measured off on the edge of the circle. This is called the arc length. So S stands for the arc length. That's like the crust of the pizza. R stands for the radius of the circle. And again, if the radius matches the arc length, then the angle that has been formed right here has to equal 1 radian. Now there's a formula that we're going to be using when we're dealing with this comparison. We're going to say that theta is equal to our central angle. Our theta has to be measured in radians. It's going to be equal to S divided by R, the arc length divided by the radius. So of course, if S and R are equal to each other, theta would equal 1 radian. Now, very often we're going to want to rewrite this formula to solve for one of the other variables. So for example, if we wanted to know how long the arc was, if we wanted to know S, which is the arc length, we would multiply together theta times R. Now, one thing that's really important to note is that the angle theta must be in radians. This formula is not appropriate if I'm using my angle measured in degrees. So radians essentially measure the total number of radii that have been traversed around the circumference of a circle in a given rotation. Based on the circumference formula of a circle, there will always be 2 pi radians in one full rotation. So again, 1 radian is equal to the angle that is created when the angle that we've chosen has the arc length equal to the radius of the circle. So when this measure right here, the radius, equals this measure right here, the arc length, the angle that we have drawn has to be equal to 1 radian. So in the following example, we're going to talk about how we can go back and forth between these two quantities. Let's start up though with example number 1. So example number 1 says, use the formula above to answer each of the following questions. So the formulas that we are referring to are called the arc length formulas. It's really important that you memorize one or the other form of this formula because this is not on our reference table for the Regents exam, And it is one of the harder ones to remember. It's not a hard formula to use, it's just not used that often. So it's really important that you remember every time I'm talking about arc length, I'm going to refer to this formula. So for part A, it says determine the number of radians that the minute hand of a clock passes through if it has a length of 5 inches and its tip travels a total distance of 13 inches. So, for example, if I've got a clock formed by a circle here, and I know that the hand of the clock, that arm is equal to 5 inches. If that arm of the clock goes through a distance of 13 inches, and I'm not measuring exactly how much that's going to be, my question is, what is that angle that we have created? So I know that the red is measuring, I'm sorry, I've said that backwards. The red is actually measuring the arc length, and the arc length is S. We know that distance was equal to 13 inches. So using my formula, since I want to solve for the angle, I want to use the one that has theta by itself. So theta is equal to S divided by R. Now the S was how far the tip of the hand of the clock traveled, 13 inches. We're going to divide by the radius. So basically we want to know how many radii are in the arc length. When I do that division, I get that theta is equal to 2.6, and that's going to be in terms of radians. I can abbreviate radians as RADS. Now, here's another example, a pendulum. So a pendulum is something that is swinging. Let's say I've got my pendulum here, and it's swinging along an arc so that now it ends up over here. So if a pendulum swings through an angle of 0.55 radians, so the 0.55 radians is going to be this angle right here. What distance does its tip travel if it has a length of 8 feet? So there's the length of the pendulum. Now if this were part of a whole big circle, so for example if my circle went all the way around like this, that 8 feet would actually form the radius of that circle. So the length of the pendulum and the radius of the circle would be the same. I know the central angle to be 0.55 radians. So I'm going to be solving for the S this time. So I'm going to use the second formula, S is equal to theta times R. So S is equal to 0.55 radians multiplied by 8 feet. And what happens here is I get S is equal to 4.4 feet. So that's how far this pendulum has traveled, the tip of the pendulum. So my answer, 4.4 feet for the arc length. And again, I often think of that as like the length of the crust on a piece of pizza. In example number 2, it says, consider 1/2 of a full rotation. So let's make a few notations here. I know that in a circle, so if I've got one circle, a circle is equal to 360 degrees, going all the way around. The angles would add to 360 degrees. Now, because we know that that's actually equal to 2 pi radians. So 2 pi radians is equivalent to going 360 degrees around the circle. If I take half of that circle, then all the pieces here will be divided in half. So 360 degrees would be divided in half, and I'd get 180 degrees. So that would be half of a circle. But if I take half of 2 pi, that's giving me pi radians. Now, of course, I also know that this is like doing the circumference of the circle. So going all the way around the circumference would equal pi times d, or 2 times pi times the radius. So that's another way that I can look at the rotation going all the way around. Now let's even divide this circle up a little bit more. If I've got a 30-degree angle, Well, I know every circle has 360 degrees. So 30 over 360, how much of the circle do I have here? That would be 1/12 of the circle. So if I have 1/12 of the circle, and to go around the whole circle, it's going to be 2 pi radians. When I take 1/12 of 2 pi, that's giving me 2 pi over 12. It's just an equal sign there. So I can cancel the 2 and the 12, and I can get pi over 6 radians for the equivalence to 30 degrees. So 30 degrees and pi over 6 radians are just two measurements for the same exact quantity. So 30 degrees and pi over 6 radians are equivalent. So we're going to need, just like we'd have to if we were going back and forth between inches to feet, or between feet and yards, or even between inches and centimeters. We have to have the conversion factor. So we're going to write it two different ways depending on whether we're trying to convert from degrees to radians or from radians to degrees. If I'm starting with degrees and I'm trying to convert over to radians, what we are going to do is take our angle that is measured in degrees and multiply it by pi over 180 radians. And when we do that, we're going to see that there's going to be some cancellation with that 180 degrees. If, however, we're going from radians to degrees, we actually use the same exact conversion factor, but we take the reciprocal. So we multiply by 180 degrees over pi radians. So in the next few examples, we're going to see exactly how to use these conversion factors. And in class, we'll do some practice, but it's really important that you do the practice that I'm giving you today so that when you get to class, you can see how you've done these and practice some more. So in exercise number 3, it says, let's convert each of the following angles that are given to us in degrees. Let's convert them into radians. Express our answers in terms of pi. So we said that when we're going to radians, we're going to multiply by our conversion factor of pi over 180 degrees, and that's going to be pi radians over 180 degrees. So I always remember that if I'm going into radians, I want my pi radians in the numerator of my conversion factor. So let's start with our 90 degrees, and let's multiply by our conversion factor, which is pi over 180 degrees, and again that's pi radians over 180 degrees. Where possible, I do some cancellation. So I'm going to say that 90 degrees goes into 180 degrees 2 times. So that's going to give me an answer of pi over 2 radians. Let's try part B. I've got 120 degrees and I want to convert over to radians, so we're going to multiply by pi radians over 180 degrees. Let's cross cancel. 120 and 180 can both be divided by 60. So 120 divided by 60 is 2. 180 divided by 60 is 3. Now another way of doing this is to put it in your calculator as 120 in the numerator divided by 180 in the denominator, and then convert to fraction form. But then don't forget about your pi radians that you're going to end up with in your answer. So this solution, this conversion, would give me 2 pi over 3, and again that would be radians. And for the last one, let's go 225 degrees and multiply by pi radians over 180 degrees. What's really happening is our degrees are cross-canceling as well, because I'm starting with 225 degrees and I'm dividing by 180 degrees. Now again, if you don't see the simplification of this fraction, use your calculator and just do that division, 225 divided by 180. Really what's happening is we can divide the numerator and denominator by 45 degrees. So 225 divided by 45 degrees is giving me 5. I'm going to keep that 5 pi radians. 180 divided by 45 is 4. So that's 5 pi over 4 radians. Now let's go the other direction. So now we are starting with radians and we want to convert into degrees. So the only thing that changes is that we're going to use our conversion factor, but we're going to take the reciprocal. So when I want to convert into degrees, I'm going to multiply by 180 degrees over pi radians. And again, remember that we were starting with radians over here. So our radian units can cross-cancel, but our pi's can also cross-cancel. I'm going to go ahead and cancel numbers as well. 6 goes into itself once, 6 goes into 180 30 times. That's going to keep the degrees in the measurement. So 5 times 30 degrees, 150 degrees. So 5 pi over 6 radians is equivalent to an angle of 150 degrees. For 3 pi over 2, let's again multiply by my conversion factor, 180 degrees over pi radians. Now they're both radians, so I'm cross-canceling the word radians, but I'm also cross-canceling the pi that appears in both the numerator and denominator. Go the other direction, and 2 goes into 180 90 times, but that's 90 degrees. 3 times 90 degrees, 270 degrees for our answer. An angle of 270 degrees is equivalent to an angle of 3 pi over 2 radians. Let's go to 3 pi over 4. This is radians. So 3 pi over 4 radians. Multiply by the conversion factor, 180 degrees over pi radians. And we can cancel off the word radians, cancel off the pi's because they're equivalent numbers. 4 goes into 180 45 times, and again that keeps the degree symbol there. 3 times 45 degrees, 135 degrees. Now I want you to take a few minutes and do the you try it examples, and then come back after you've done the problems and check with my solutions. Okay, you try it number 1, you should get 240 degrees. I canceled the pi's, I canceled the radians, and 3 went into 180 degrees 60 degree times. And number 2, I can cancel the 180 and the 315. They can both be divided by 45, so it's going to give me a 7 on top and a 4 on the bottom. And you'll notice that I'm keeping this time the units of radians. So I do have pi in my answer. It's 7 pi radians over 4, or 7 pi over 4 radians. Now sometimes we'll be given an angle where the angle is measured in radians, but it doesn't include a pi in that radian measurement. And that's perfectly okay. In example number 5, it says convert each of the following radian angles, which are not in terms of pi, over 2 degrees. So we are given that these are radian angles, and we want to convert them into degrees. So you'll notice that when I have radians, it's not always going to say pi in my measurement. So we're going to do exactly the same thing that we did on the past examples. So 5.8 radians, we're going to multiply by, we want to get our answer to be in terms of degrees, so we're going to multiply by 180 degrees over pi radians. Now what actually only cancels here are the units radians. I then am going to go to my calculator and I'm going to multiply 5.8 times 180, but then I'm going to divide by the key on my calculator that says pi. So 5.8 times 180 divided by pi. And then we're going to round our answer to the nearest whole number degrees, so that's 332 degrees. For B, I've got 4.2 radians, and I'm multiplying by 180 degrees over pi radians. I again see that the radians, the units, are going to cross-cancel. And then let's multiply 4.2 times 180, divide by that pi key, and then round my answer to the nearest whole number, 241 degrees. Lastly, negative 2.5 radians. I'm going to multiply by 180 degrees over pi radians. I'm going to cancel the radians from both, and then on my calculator multiply negative 2.5 times 180, then divide it by pi, and that should give me 143 degrees to the nearest degree. Now exercise 6 is very similar. It says an angle drawn in standard position has a radian measure of 2 radians. And we want to know, where's the terminal side of this angle going to be? Which quadrant? So let's start with our 2 radians. And let's convert it over to degrees. So I'm going to multiply by 180 degrees over pi radians. So once again, the radians are going to cross cancel. On my calculator, I'm going to say 2 times 180, that gives me 360 degrees. But then I'm going to divide by pi, and again, I'm using the pi key on my calculator. This is giving me, if it's rounded to the nearest whole angle, whole number, 115 degrees. Now this question asks, in what quadrant is this angle going to end? So obviously it's much easier to decide the quadrant if I've got the degree measure. So we all know our quadrants by now. In quadrant 1, I'm going angles from 0 to 90. In quadrant 2, we've got angles from 90 to 180. In quadrant 3, we've got angles from 180 to 270. And in quadrant 4, we're going from 270 up to 360 degrees, which is actually equivalent to 0. So where's 115 going to be? Remember, our initial side always has to be along the positive x-axis. And we're just going to go a little bit past the 90 degrees. So right here I have an angle of 115 degrees. And that, of course, is quadrant number 2. And I think I mixed up the order on our multiple choice when I typed it here, so it should be choice 2, which says quadrant number 2. Well, thanks for practicing with radians and degrees. This is something you're going to be using for the rest of your math career. So let's start working on converting between degrees and radians. Have a great night, and we'll see you next time.